Faraday's integral law shows how a voltmeter reading induced by magnetic induction at the terminals of a coil provides a measurement of the magnetic flux density. In this experiment, the contour C is traced out by the wire in this coil, so that the surface S is the area having the entire length of the coil as its edge. In this coil, the surface area S is 8 centimeters by 21 centimeters multiplied by 20 turns. We will use this coil with Faraday's law to find the magnetic flux associated with current in this wire. The upper trace of this oscilloscope records the electromotive force of voltage at the coil terminals. The lower trace is the current in the wire, measured by the voltage drop across a 1 ohm series resistor. With the coil rotated so that it links no magnetic flux, no voltage is seen. With the coil now placed so that the magnetic flux passes perpendicularly through the coil, the maximum signal is recorded. With the coil straddling the wire, the flux passing through the coil in the upper section is oppositely directed to the flux through the lower section. With it symmetrically positioned, the net flux is 0, so the measured voltage is 0. The scope traces are triggered on the wire current, the lower trace, so we can see the change in phase as the coil is moved from below the wire to above the wire. The lower trace current is 90 degrees out of phase with the upper trace induced voltage. This is because the coil voltage is the time rate of change of the magnetic flux, and hence of the time rate of change of the current. The coil voltage is 90 degrees out of phase with the current.